So this is the example of the detection of surface defects in the products in industry. But you can imagine as a detection of changes in aerial images or satellite images, for instance, right? And what we are currently doing when we're talking about this supervised learning is that you tell, okay, this image here does not contain any defect. This doesn't contain any defect as well. Here we can see a defect and you provide segmentation mask of the defect, right? And here is a defect as well, right? So this is fully supervised. On the other part of the spectrum, you have unsupervised learning where you don't have, where you only show the images without defects, right? And of course, then you can have a mixture of both, that you just tell, okay, there is a defect in the image, but I don't know where it is, right? Or mixed supervision, where for a part of the images you tell and show where the image is, while for the part of the images you just tell that there is a defect, right? And what we showed is that we can get similar results also in this unsupervised manner. This is the direction we want to go, right? Or even what you want to have is to show a number of images, and some of them contain defects, but we don't know which of them contain defects. All we know is that, I don't know, 95% of the images do not contain defects. And this is a even more difficult problem. But transferring this domain to, let's say, remote sensing domain, this is what we discussed before. This is something that we would like to have, really, to remotely observe one area and to learn regular changes in appearance due to seasons and weather and so on, and detecting some irregularities like fire, right, or new building or something like that. And since we have a really huge amount of data, satellite data, I believe this can be done, right? Yeah, but this is the architecture that we used yesterday. I showed that how to use that for supervised learning, but in similar way can be used also in this mixed supervision manner. But something I would like to show here is actually Vityan's work, right? So this is about unsupervised learning, exactly what I was mentioning before. So it's again about the defect detection. All you do is, so you don't show any defected sample in the training stage, only defect free. And you tell the system, listen, this is a variety of the objects that don't have any defects. Train all possible appearances of these objects, and this is something that's okay. If you have discrepancy, if a novel image that is shown does not conform to this distribution of those images, then it is probably defective. And this is how he solved the problem. Basically, what he tries to do is to reconstruct. So he shows a number of the images, defect-free images in the training stage, and tries to learn to reconstruct those images. And since there is no defect shown in the in the training stage, we hope that the defect cannot be reconstructed. So once you get one defected image like this one, you see like this peel with this crack here. And since this crack was never observed during the training stage, it cannot be reconstructed. And this is, you can see that like this heat map here shows probability for every pixel to be defected, right? And blue is 0 and the red is 1, and everything else is in between. And you can see that the system, although it didn't see any defect in the training stage, it can nicely detect those defects that cannot be modeled, since the model was trained only on defect-free images. And we have a number of approaches in this direction, and it can really be observed tremendous progress in the last 2 years. Basically, this data set was published 2 years ago, right, Vityan? Am I right? or let's say in 2018?
No, it's 2019, I think.
2019. Okay, so it's even less. It's really less than 2 years ago. And in the paper, when they published the paper, the results that they published using state-of-the-art methods at that time were quite poor, right? So, but nowadays, the data set is actually saturated. So, Vityan, what you get, like 98% or something like that of the text.
Yeah, I think when they published, it was around 80% or something like that.
Yeah.
And now it's around 90, 80 or something like that.
So basically so that's why I want to say, so this is now the trends in deep learning now are really going that direction to try to go beyond supervised learning, right? So and this is one way how to do it, right? To try to learn how to reconstruct regular appearance in order to detect something that can be reconstructed as irregularity. And there are a number of approaches that do that, and this can be relevant, especially for this remote sensing applications. Another way how to go beyond supervised learning is reinforcement learning. This probably can't really be applied, if I think well, in your domains, since in this case, what does reinforcement learning mean? It means that it tries to learn automatically. So system, let's say we apply that to robotics domain. So the goal in this case, you see the mobile robot that wants to reach the goal, okay? And then when the goal is reached, it moves and it reaches it again and so on. However, it should not hit any obstacle, okay? And this is like a nice application for reinforcement learning, since the robot can, at the beginning, the robot doesn't know anything about how to do this, right? And then it tries something, and if it hits something, it is penalized. If it comes to the goal, it is awarded, okay? So you don't need to give him any label. It's just the final reward that actually the system gets. And by doing that, you can let the robot do that. Of course, you'll not let the robot hitting obstacles and walls all the time. That's why we train the model in simulation, in this simulation as you see here, right? And all we tell the robot is whether it succeeded or not. Without any labels, we don't tell him, go in that direction. If you see something in front of you, turn left or turn right or something like that. Everything it learns automatically, right? Just by getting these rewards and punishments. And then we can do this in simulation, but then it works, since we do heavy randomization, we do that, it works on the real robot, in the real environment as well. So this is another way to go beyond supervised learning. However, there is another thing that I want to mention with respect to this learning, and we always get to this point at some point. What should be learned? We're talking 3 days about deep learning, but in reality, like when in the humans, we are really a very good example of learning. We are learning all the time, but not only in the primary school and faculty and so on, but in everyday life, we are observing what is happening in our environment, and we learn, we improve our knowledge and experience and skills on top of that. So what about robots, about the system? What shall we learn? What shall we program it? What program, hand code, what shall we program in our programs that drive those robots? And there is a lot of this discussions, what should be innate and what should be learned. And for that particular case that I shown in the previous slide, the robot learned everything from scratch, right? At the beginning, it didn't have any notion about the obstacles and about, I shouldn't hit the obstacle. He got that notion only when he hit it, and he got the punishment because of that, right? So, but we know for the robots that they should not actually hit the obstacle. So it's if you can hard code that, if he can put that in the genes of the robot, why not, right? And what it turns out in many situations is that we can constrain the problem by giving to the solution by hand coding some a priori knowledge that we have, and then from then on train to work better, right? In the case that we discussed previously with that 1,000 different bands in that hyperspectral image, right? If you know that, I don't know, 900 of those bands are useless, then you just discard them and you train only on the last ones. If you have this a priori knowledge. Of course, if you don't have, then it's up to machine learning to find that out, right? But let's say in this case of the robot, there exists a lot of engineering approach how to avoid obstacles, but they have their own problems, right? And typically those problems are that it's difficult to estimate, let's say, the amount of some parameters, the value of some parameters that are actually used to avoid the obstacles. So what we did in this case, we use this classical engineering approach, but then use this data-driven learning approach to learn those parameters, right? So we brought best of both worlds together. So my message is, if you can solve the problem by a small hammer, right? So by using some a priori knowledge, and then just a part of the problem use deep learning, like the part that is really data-driven. Do that. Do not, use a big hammer to solve everything from the scratch by deep learning if it's not needed. So, although I'm repeating myself for 2 days that deep learning can, can solve all the problems, is not almighty. So, if you can solve the problem with simple methods, do that, right? And if I just divide all the problems that exist in the world to different with respect to complexity. On one hand, we have very simple problems, right? The well-defined problems that are really based on certain rules, right? I don't know, in the football, for instance, right? Determining whether there was a goal or not, right? It's from the rule-based, it's quite easy. If the entire ball crosses the line, it's a goal. Otherwise, it's not. So you don't need really thousands of training samples to see whether to show to the system whether there is a goal or not. You just program that in, right? You can just estimate where the ball is, estimate where the line is, and if the ball is across the line, then that's goal, right? So these are like simple, well-defined problems. While on the other hand, you have this very complex, vaguely defined problem. So you can't really, for instance, we had such an example today. We have like ski jumping in Planica, for instance, right? It's quite clear how to define the distance, right? You just look where the athlete landed, and that's quite clear rule how to define that. But for getting style points, the rules are quite soft. It should be elegant, symmetric, nice, and so on. You really can't program, can't make a hand. You can hand wire the rules how to do that. Like the judges, they use their own judgment, right, to get him like 20 or 18 points or something like that, right? And what you can do in this case is really to get a lot of decisions from the judges and try to learn how they did make these decisions. And we did also some such application using machine learning to do that. So it's actually there's a spectrum of different problems. And what I'm saying, and if I divide those problems to 4 categories, they are rule-based, routine solutions, rule-based solutions, data-driven solutions, general, and some general intelligence that has to be used to solve the problems. And deep learning is here addresses these data-driven solutions, right? It can also improve some rule-based solutions. It can also be used to derive some general, some solutions that require general intelligence. But in practice, here we need to have more powerful, more intelligent techniques to solve these solutions. And here we don't need actually deep learning as such. right? So my take-home message would be, if you have problems that can solve with simpler methods, use simpler methods. But deep learning is really strong solution for such kind of data-driven problems. And okay, it's noon already. So can I spend 5 more minutes? Or
yes, of course.
Okay,
of course.
Because this slide is really good to understand how we actually develop such kind of applications. So first, I've been repeating myself for 3 days: data, data, data. We must have enough data and representative data and correctly annotated data if this is a supervised problem. So first, you really need to make sure that you have good data, and then you have to devise appropriate deep architecture, proper backbone, loss functions, and all that stuff. You typically, I would say, start with some, as Vityan said, with some standard architecture that are already there, right, to get some results. But if this does not suffice, then you need to tweak this architecture, to add additional heads, to change the loss function, to combine something. So you have to work on it, right? And as we saw in the previous examples, we really need to learn to set the parameters in order to make them run correctly. And if we find out, and typically we do, right, while learning, we see that the data is not good enough, right? There are some errors in labels, that some images, some appearances are underrepresented, right? And then you just need to collect more data. I remember 2 years ago, I was at some conference, and Andrei Karpathy exposed how do they do that for autonomous cars, right? If something does not go well, the first thing they do is they call that data, the service that is like their group that is responsible for data, and they just ask them, please provide us more and more data to improve our model. So it turns out that having good data makes better. You can make better improvements by providing more appropriate data than by tweaking architecture from some point on, right? So this loop you will probably do, right? Once you develop the system, then you probably want to update the data in order to make the system work better. And of course, once it works fine, you want to be efficient enough. So especially if you want to have the real-time operation of your system, and sometimes you then find out that maybe your implementation is too slow, so you go one step back in order to make it work, and then you deploy the system that you have, right? And one thing that is very important here is that once you have the running system, it's not difficult to just provide new data to improve the system itself, right? I emphasized that yesterday already, right? And in your cases, I can imagine that this is really can be of great importance, right? You deploy the system, it runs, but then you can improve through time. So it's not like in old days when you developed some system and it was there. So if you want to improve the system, you have to hire that company again to reprogram it and so on. Nowadays, you can improve the system by offering it new data, and that's a very good property of such data-driven solutions. Okay, I wanted to show this slide just to make that clear. I was talking about that even before, right? So this is quite a common curve, right? In a very short period of time, let's say, I don't know, 20%, you'll get quite well done solution, right? Let's say, looking at those ship detection previously, it took Vityan probably like half an hour to set up the system. Okay, maybe I'm exaggerating a little bit, but still, taking a pre-trained model, train it on on new data, and you get quite good results, right? But the problem is, for the last, let's say, 20% of the solution, you need much work to be done on it in order to make everything work smoothly. So, which means do not be very happy too quickly. but do not give up if in some time you don't find a solution, right? So that's definitely true for such kind of development. Of course, it could be 90-10 or 99-1, or in some cases 60-40, right? It depends on the complexity of the solution, right? And yeah, after you do a lot of projects, then you get, you mentioned about setting those parameters and so on. It's not really, you can't that in advance. There is no prescription how to send those parameters. But after you develop a number of architectures, then you get experience and you have better feeling how to do that. But at the end of the day, you optimize those parameters to get the optimal working solution. And what I always say, you can use the deep learning as a black box, right? But it's very useful to know what's behind that. What are the small boxes inside the black box, and what's inside those small boxes? So if you want to really go to the edge, right? You need to know what is there, right? And even looking how complex solutions can you solve, right? You can solve a lot of problems by considering learning, right, as a black box, right? But if you want to solve the really complex problems, then you have to know a little bit more about that. Okay, but this is the final slide that I wanted to say. I really believe that this, you see, Predrag, data-driven learning-based solutions are really key enabling technologies of a lot of areas, right? And in the past, it was not the case, right? I have to admit, I'm in this field from a number of years, and I don't know, 10 years ago, we couldn't solve a lot of problems reliably. In that time, we could solve the constraint problems, right? When you have the control under illumination, under the environment, under background, and so on. In that cases, there were quite a lot of good, let's say, machine vision solutions that work, right? But nowadays, these methods became really much more robust, and they can really work in real world, right? So, and what I would really like to emphasize for this audience today, there are new opportunities and also for collaboration between different disciplines. So deep learning is very interdisciplinary. It can improve a lot of interdisciplinary problems, right? So I wanted to present a number of solutions today, and yesterday and 2 days ago. Not a lot from your area of expertise, I'm afraid, but I hope that you can see how those different disciplines can be combined to improve your problems, actually, to solve the problems that you're facing with.